So welcome friends. So today we discuss the problem which is written here. So does there exist a real function which is continuous only on a given subset f of R? So we shall require some result in going to this one. We will see partial answer of this question. So let us first recall some result about continuity. So let me write theorem. It is this one. So let f, I am writing a general result which is also true for a function from R to R. So let f from xd to y rho be a function where xd and y rho are metric spaces, and let say a from x, then it is true that then f is continuous at a if and only if f of n converges to fa. Whenever n is a sequence in X converging to A. That means whatever sequence n of elements of X we take which is converging to A, then we have f of an converging to, or f of an converges to f of A, whatever sequence we take. So this result is helpful to us in proving many times discontinuity. I mean, if you want to show that f is not continuous at A, then what we should do? We should find out a sequence, say an, some sequence an which is converging to A, but f of an does not converge to fa. So I am writing that. So this implies the following. This implies that, or the above result implies that if n is a sequence in X such that n converges to A as n tends to infinity, and f n, this sequence, does not converge to f of A, then f is not continuous at In fact, the converse is also true, because the above theorem says that this happens if one statement holds if and only if the other statement holds. But we shall be requiring only this when we go ahead. Okay, so before going further, again let us see one more result. This we are going to use in getting a partial result of the statement or of the problem which we have stated. Theorem. So let f and g from R to R be continuous, and let, by using these two functions we define a new function. We are calling it h of x, which is defined by this way. It is f of x when x is rational, and we are defining it to be gx when x is an irrational. Right. This is the way we are defining the function h of x. Then the result is this one. Then the set of continuity of the function h is, I'm just writing this way, ch to be all those x in R such that f of x equals g of x. Means whenever two functions f and g from R to R are continuous, and by using those two functions if we define the function h by this way, that is h of x is fx when x is a rational number, h of x is gx when x is an irrational number, then the set of continuity of this function h is precisely this set ch. Right. So let us see the proof. Proof is much easy. First we show that if x is in ch, then the function h is continuous, and then we show that if x is not in ch, then h is not continuous. So we start with any x, let x be in ch. We start with any see what we want to show, h is continuous at the point x. So we take any epsilon positive. Take any epsilon positive. The functions f and g, they are continuous at every real number. So in particular they are continuous at x. So since, let me write this way, f and g are continuous at x, we get some delta positive such that mod of fx minus fy less than epsilon and mod of gx minus gy less than epsilon whenever mod of x minus y less than delta. Obviously y is a real number, right? Actually for f we get delta 1, for g we get delta 2, and then take delta to be minimum of this delta 1 and delta 2, right? Okay, now what we are going to show is that if mode of x minus y is less than delta, then we show that mode of hx minus hy is less than epsilon. Right, so let us see how we do it. So take any real number y, and we also take mode of y minus x is less than delta. See, okay, as x is in CH, what do we get? Fx is same as g of x, that is same as h of x. That's fine. Right, because y is a real number, we are having two possibilities, either it's rational or irrational. Let me write that. If y is in Q, then what happens? Let us see. Then mode of hx minus hy. Now because we have written here hx, so in place of hx we can write either fx or gx because they are all same. So we are writing f of x, and because y is rational, h of y is same as f of y. Right. But it is known to us that whenever mode of x minus y less than delta, we have mode of fx minus fy less than epsilon. So this is less than epsilon. And if y is an irrational number, then hx minus hy. So hx we may write as g of x, and hy, because y is irrational, hy is same as gy, and again by continuity of g it is less than epsilon. And thus what we have shown, that mode of hx minus hy is less than epsilon whenever mode of x minus y less than delta, and that means h is continuous at x. And which x have we chosen? We have chosen x from CH, and thus what we have shown, thus h is continuous at every point, of CH. And our aim is to show that the CH is precisely the set of continuity of H. That means we need to show that if X is not in CH, then H is not continuous at the point X. So let us also show that. So let X be a real number and X is not in CH. And because X is not in CH, by definition of CH, Fx not equal to g of x, because CH precisely contains all those x for which fx equals gx. So x is the real number. Again we are having two cases, either x is rational or x is irrational. So let us take first case, let x be a rational number. Okay, so we use the first result here which we have stated. If we want to show that the function is not continuous at a point, then we are going to produce a sequence which is converging to a point, but h of that sequence does not converge to h of that point. So x is in Q, then what do we get? Then h of x, that is by definition f of x. It is known to us that the set of irrationals is dense, so we are going to get a sequence of irrationals converging to x. So let xn be a sequence in R minus Q such that xn is converging to x as n tends to infinity, and as g is continuous, what it will give? It will imply g of xn converges g of x as n tends to infinity. But that means what is g of xn? Because xn's are irrationals, g of xn is same as h of xn converges to gx as n tends to infinity. And what do we have? We have gx, which is not equal to f of x, but f of x is same as h of x, and that means what we have shown, h of xn does not converge to h of x. That means we found a sequence xn which is converging to x, but h of xn does not converge to h of x. And the case for x in R minus Q, I mean, you can do a similar way. So you may write those things here, and thus what we have shown, therefore h is not continuous at x. Right now, as I said, if you take the second case, then you may give a proof similar way. So I'm not writing that proof. The second case, namely, let x be in, because when x is a real number, it is either rational or irrational. We have shown that if x is rational, then h is not continuous at x, and similarly If x is irrational, then you can show that h is not continuous at x. Okay, and that you will do. And thus we proved the result. That means if we are given two functions f from R to R, f and g from R to R, which are continuous, and by using that, if we define a function h of x by this way, h of x is fx when x is rational, h of x is gx when x is irrational, then the set of continuity of h is precisely the set CH. Right. Now if somebody asks you that give me a function which is discontinuous only at 0, discontinuous, then it's easy. You may probably give this graph. Just we are breaking continuity at 0. If somebody says give me a function which is discontinuous at the points 0, 1 and 2, then probably, it is much easy. We are going to break continuity. Here it is 0, 1 and maybe let me do this way. This one is not included, no? You people know all this. So this is a function. The second one is a function which is discontinuous only at 0, 1 and 2. And the first one which is discontinuous only at 0. But now can we give an example which is continuous only at 0? Let us see how we do that. So we are going for examples. We will write first. Give h from R to R, which is continuous only at 0. Let us see how we do it. Take f of x to be x and g of x to be 0 function. This is not the only way, but this is one of the ways, yes, for all x in R. For all x in R. One more thing, let me tell you. In the definition of h, we have taken hx to be fx when x in q and gx when x in R minus q. You can also change the roles. That means you can define h of x to be g of x when x in q and h of x to be f of x when x in R minus q, but the conclusion will be the same one. Okay, so we have taken fx to be x for all x in R and gx to be the 0 function. Then obviously f and g are continuous on the whole real line. Right. Take h of x to be f of x when x in q, g of x when x is in R minus q. This is same as x when x is in q and it is 0 when x is in R minus q. Right. So by above theorem, what do we get? Okay. So here, what will be CH? CH will be all those real numbers x in R such that fx equals gx. That means it is the set of all real numbers for which x equals 0, and that is precisely singleton 0, and thus what we have shown. Thus H is continuous only at 0. I think you understood this one. We constructed two continuous functions which are agreeing only at 0. So there is nothing special in 0. If we want a function which is continuous only at a, then what do? We take fx to be x minus a, g of x to be 0, and do the same process, and then we will get a function which is continuous only at the point a. Right. Here we consider the special case when a is 0. Right. Now if I want a function from R to R which is continuous on a given finite set only, let us see how do we do that. So give H from R to R which is continuous only on a given finite set, non-empty set we are taking F. So let us see how do we do this. Because F is a finite set, we may write say F to be A1, A2 up to AN. Okay, define f of x to be x minus a1, x minus a2 up to x minus an. It's a product, or it's a polynomial of degree n, and g of x to be the 0 function for all x in R. These are the functions, f and g, they are defined this way. Because f is a polynomial, g is a 0 function, that is also a polynomial, so they are continuous. Then f and g are continuous functions on the whole real line. What we do, take h of x to be f of x when x is a rational number, and we define it to be g of x when x is in R minus q, and this is same as x minus a1 up to, means multiplied by, up to x minus an for x in q. It is 0 when x is in r minus q. Okay. Then by again above theorem, what is the set of continuity of H? Okay, then the set of continuity of H is what? CH. That means all those real numbers x for which f of x equals g of x, and that is same as all those x in R for which x minus a1, x minus a2 up to x minus an is 0, and it is known to us that if the product of n real numbers is 0, then at least one of them has to be 0, and by using that we get this set is precisely a1, a2 up to an. That means what? We have found a function h from R to R which is continuous only on this. Means if you take any point outside f, then h is discontinuous, and it is continuous at every point of capital F. Right. So we shall discuss some more problems in the next video, and if you have any doubts, questions, or if you want me to discuss some problems on some different topics, you may write in comment. We'll see those. Thank you very much.